Well, today we will talk about the zero age, zero age main sequence structure. This is also known as ZAMS. So, its structure basically we will discuss in today's class, and also thereafter we will talk about the evolution of first high mass stars and later on low mass stars. Now, you see, what is this ZAMS? First thing, you see, when hydrogen begins to fuse into helium in the core of the star, then it is considered to be ZAMS. For high mass stars, what happens is that for high mass stars, what do they have? They have very high densities, so density is high, and also this high density and pressure is also high in the core, and this causes the CNO cycle to dominate the hydrogen burning process, and as a result the core is convective. Okay, now you see, as hydrogen burning progresses, the number of nuclei in the core decreases, and so the mass fraction changes. So let us now talk about the mass fractions. So, mass fractions, how they change with hydrogen fusion or hydrogen burning. Now let me write down the expression you must remember. So it was 1 by mu for ions, then for electrons, and this is equal to basically twice x plus 3 by 4 y plus 1 minus x minus y, right? And then there was an average term. What was that? It was 1 plus z by a, averaging. This was the result, where of course we have used the fact that x plus y plus z is equal to 1. Okay, now if we use this to eliminate the z from the above equation, and also if we note that this is approximately half for nuclei, then right, for low mass metals basically, nuclei, then what we can do is write this equation, this expression for mass fraction, in a somewhat different way. So what is this? We can write, what we can write is this expression. You see, 1 by mu is equal to half plus 3 by 2 x plus 1 by 4 y. So using average and eliminating z, this gives us this. Now what happens is that as your hydrogen fusion continues, what happens is x decreases, and of course helium is produced more, y increases. So what do you see from here? So you can infer that as such a things happen, that means as x decreases and y increases, what you can say, look into the numbers, coefficients, basically mu increases. Okay, now during the hydrogen burning, the gas at the core, so during hydrogen burning, core gas, it can be treated as ideal. Okay, and so we can write P is equal to R by mu into rho T. Okay, fine. Now you see what happens is that an increase in this mu, it results in a decrease in pressure. So increase in mu causes decrease in pressure. Now this decrease in pressure results in contraction of the core and subsequent rise of density and temperature. So we have got that cycle, thermal stability kicks in, right? So decrease in pressure means core contract, then rho and T increase, right? So this means pressure is restored. Okay. Now this is a consequence. This is basically consequence of what you can say secular thermal stability. I have said this thing many times. So basically secular thermal stability. Okay. Now you see the increase in density and temperature also produce an increase in, this also causes an increase in the nuclear energy generation rate or nuclear burning rate, basically which causes an increase in the luminosity. Now, do you remember how the nuclear burning rates were? So, I think you must remember for the CNO cycle, the epsilon, the burning rate was proportional to T to the power something 19, whereas for the PP chain, again we are considering H burning only. Okay, for the PP chain, this was proportional to T to the power 4, right? So consequently, there is a substantial increase in the luminosity of high mass stars, right? So as a result of this, there is a substantial increase in luminosity for high mass stars as a result of a small change in core temperature. Why? Because for the high mass stars it is the CNO cycle which is dominant, and look at the power 19. Just a small change will have huge impact on the luminosity, since the nuclear burning rate will be changing by a large amount. Okay, let me give you a sort of demonstration through a simple discussion on an example. Now let us suppose an example. Okay, now let us suppose that the core contraction associated with an increase on mu is homologous. That means core contraction is homologous associated with increase in the mean molecular weight mu, so that throughout the core, as a result of which R changes by a very small amount, R plus delta R. Now, if the energy generation rate suppose this is given by this value, say Q. Instead of epsilon, I am writing Q. Suppose this is given by this value. Q is some constant Q0 into rho into T to the power beta. Okay. Now, what can we say if such a thing happens? Then, as a result of this thing, what can we say regarding the fractional change in energy generation? So, this is the question. What can we say about this as a result? Can you do this? Let me show it to you how you can do that. So, you see, let's start with this, our familiar expression. So, rho is equal to 3m by 4 pi r cube, and as a result we can write del rho by rho is equal to minus 3 del r by r. Now let us assume that the core is described by ideal gas. So core is described by an ideal gas. Okay, so that we can write. Okay, so what are we going to write? Now before that, let me again write down this equation. You remember this we derived during our discussion on thermal instability regarding the change in density and temperature, and this was a generic equation. Now in this generic equation that we have derived for the ideal gas, let us put A is equal to 1. This we discussed, remember, previously. And B is equal to 1. So that we will get from here. So we will get 1 by 3 del rho by rho. This is basically, del, right? This is equal to del T by T. Now if this is result B and previously we have this result A, then we can combine the two of them. So using A and B, you see what we get is this result, del Q by Q is equal to minus 3 del R by R minus beta del R by R, and this is finally, you can write minus 3 plus beta into del R by R. So this is your change, right, in the nuclear burning rate as a result of this change in the radius. So this is quite interesting application. Okay, so you see we have I've just shown you a very small example of the fact that there is a substantial increase in the luminosity for high mass stars as a result of small change in the core temperature, and right now we just talked about the change in the small radius, and we checked the change in the fractional change in the energy rate. Okay, now you see, since the changes in the star are occurring, so changes in star are occurring on nuclear time scale. So we can assume that the star remains in thermal equilibrium and in hydrostatic equilibrium during these changes. Okay, now as a result, both the internal energy and gravitational potential energy are separately conserved. internal energy conserved and gravitational energy conserved separately. Okay. Therefore, when the core shrinks, the envelope must expand to maintain the gravitational potential energy. So, when the core shrinks, then the envelope must expand to maintain the gravitational potential energy. Similarly, because the core temperature increases, since your core temperature increases, so the envelope must also cool. Okay, must cool to maintain internal energy. Now, as a result of these two changes, say change 2 here and change 1 here, what happens is that of 1 and 2, what happens is that the contraction and heating of core causes the surface of the star, surface of star to expand and cool. Okay, this is very interesting. Now, you see, despite the increase in L nuclear, so the effective temperature drops. So what happens is that even though despite the increase in L nuclear luminosity due to your nuclear processes, despite this, the effective temperature drops. And as a result, what happens is that the star moves off to the right and above its ZAMS location during the main sequence evolution in the HR diagram. So basically here we are talking about this main sequence. So suppose the star is over here. So what will happen as a result of this thing is that it will move towards the right and above. So along this direction the star will move, something like this. It will follow this path during its main sequence evolution. Okay, now this is a standard feature of the stellar evolution, that the radius, luminosity and the central temperature of a star increases during the main sequence phase. So standard feature is that R, L and Tc, they all increase during main sequence phase. Okay? Okay, so you must be wondering, well, what will happen eventually? Now you see, of course, what will happen is you also know. Hydrogen will not be there forever. It will be burnt out, right? So eventually, the core hydrogen will be depleted, right? And as a result, hydrogen burning in core stops. Fine. Now what? Now you see, for stars with convective cores, okay, what happens? This occurs nearly simultaneously. Because of the mixing, this will occur nearly simultaneously throughout the convective region in the core. Okay, so when the nuclear burning stops, the core quickly becomes isothermal. So this means that when nuclear burning stops, core quickly becomes isothermal. Fine. Why? As there are no new sources of heat in the core. As there are no new sources of heat in the core. See? Now what? Well, there may not be any heat sources in the core, but hydrostatic equilibrium must be maintained, though the basic principles must be maintained. So what will happen is that in order to maintain hydrostatic pressure, the core must set up a pressure gradient to support the layers above it. Right. Now, what can you say from the ideal gas law? You know, from ideal gas law, you can say that an isothermal core can only set up a pressure gradient by developing a density gradient. Remember, as why? Because of this relation or the ideal gas law. P is proportional to rho T. So, what we can say is that there is a general feature of this cessation of core burning. And what is that? The general feature is that when the core burning stops, basically we have a contraction of the core in order to produce the density gradient, right? Now, the gravitational energy released through the collapse increase the luminosity. So, during collapse, the released gravitational energy, it increases the luminosity, okay, and the temperature at the outer edge of the core increases, and as a result the temperature of outer just a second of the outer edge of the core increases enough to ignite a hydrogen, sorry, let me write it over here, ignite a hydrogen burning shell around core. Okay, so basically we have got now shell hydrogen burning. And what happens as a result? So the result, this is important, the result is that this causes the envelope to expand and effective temperature to drop. Okay, so this is interesting. Now you see how much is this is all qualitative stuff, right? Now the exact details of the ignition of the shell burning hydrogen and the collapse of the helium core actually depend upon the ability of the isothermal core to support itself and the envelope above it. And we will look into the details of this. To understand this, we have to look into the details of the isothermal core equilibrium, which we will look in our next class. Okay.